In section 7.4, we're concerned about two ideas, arc length and surface areas of surfaces of revolution. But before we can get into that, there's something we're going to need in the proof of the formula for arc length, and that's the mean value theorem, which you covered in section 3.2. And mean value theorem says, suppose f is continuous on the closed interval AB, and the function is differentiable on the open interval AB. Okay, so only two conditions there: continuity on the closed interval, differentiability on the open interval. Then there exists a number c in the open interval AB such that f prime of c is f of b minus f of a over b minus a. Okay, so f prime of c is f of b minus f of a over b minus a. Okay, let's draw a picture to see what this is doing. So this is just some generic curve. And so there's some generic curve. And I'm saying there's a, and B is over here somewhere. Okay, so this is my function f. And do you agree that my function is continuous on the closed interval AB? Sure, right? No holes, no jumps, no asymptotes. And is the function differentiable on the open interval AB? Everywhere in between, there are no sharp corners, right? Their derivative is going to exist everywhere on the open interval AB. So this function is continuous on the closed interval and differentiable on the open interval. Okay, now let's look and see what this expression is saying. Okay, assuming you have a function that satisfies those two conditions, this must be true. So there is a point C in the open interval, so at neither of the endpoints, somewhere in between, such that this is true. Well, what does this expression on the right look like? F of b minus f of a over b minus a. Well, this is the point a f of a, and this is the point b f of b, right? So they're saying f of b minus f of a over b minus a. And we're assuming a and b are not the same points, because then you'd have undefined. You have zero that's on there. Okay? Well, what is that? That's just the slope of the line joining those 2 points. So on the interval AB, if you take the 2 points there on the graph, and you could, well, I'm going to go on my writing here. That's right. Oh, I missed. Right? Right? That right there is the slope, right? Well, I'll just do that. Right? This expression on the right is the slope of a line between those 2 points, the endpoints of the interval. Right? It's called, remember from Calc 1, that's called the secant line. If you pick any 2 points on a graph and connect them with a line like that, that's called the secant line. Okay? So this expression right here is the slope of that line. Now what is this saying? Well, if you take a derivative and plug in an x value, what does that represent geometrically? That was the slope of a tangent line. So what this is saying is, somewhere in between a and b, there is a value c such that the slope of that tangent line is equal to the slope of the line joining the 2 endpoints. Now where is that here? Roughly here, maybe? Right? So I claim c is there because the tangent line there looks like that. And notice the lines have the same slope. And there could be more than one place. I said there exists a c, there could be more than one. Right? So what does the mean value theorem say again? If you have a continuous function on a closed interval that's differentiable on the open interval, then there's a value c between a and b such that the slope of the tangent line at c is equal to the slope of the line joining the 2 endpoints. That's what the mean value theorem says. Okay, so that was in Calc 1, and we're going to need that in the proof of the formula for the arc length. Okay, so just keep in mind what that says. The slope of the secant line through the endpoints, there's a tangent line that has that same slope. Okay, now these next definitions, I'm not really that concerned about, but I put them here to be complete. A rectifiable curve is a curve that has finite arc length. We're not going to find the arc length of a curve that's infinite. A function is continuously differentiable on a closed interval if the derivative is continuous on the closed interval. Remember, just because a derivative exists doesn't mean the derivative function is continuous. And the graph of a continuously differentiable function is called a smooth curve. That's everything we're going to do here is involving smooth curves and continuously differentiable functions. So everything they're going to give you is going to be like that. So don't worry about the definitions here. Okay, let's try to derive a formula for arc length. So let me draw a generic curve here. So that's under the picture here. Okay, so some generic curve, my standard generic curve. And we're going to go from, say, A to B, as always. So I want to find the length of the curve from A to B. Okay. Well, what's the game here? Right? How are we supposed to find the length of this when we don't know how to find lengths of curved pieces? Well, we're in calculus, remember, right? How did we find, when in the last lecture I reviewed in Calc 1, how do we find areas under curves? And we didn't know how to find the area under curved pieces, so what did we do? We took areas of rectangles, which we knew, and approximated. So we're going to do the same thing here. So let's chop this up, just like we did before. So A we're going to call x naught, and then we're going to have an x1 and an x2, x3, dot, 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 an xn minus 1, and we'll call B x sub n, just like we always do. And let's find those points on the graph. So that point, this point, dot, 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 this point, okay. Okay, now, I'm not assuming the partition is an equal partition. You could. Okay, so we're just gonna assume that they're not necessarily equal. Okay, now, so how are we supposed to estimate, what's a way to estimate, say, just from here to here? How can we estimate the length of the curve from here to here? Well, what's something that we know how to find the length of? A line segment. So why don't we find the line segment from here to here, find that distance, and then the segment from here to here, and the segment from here to here, and you keep going, the segment from here to here. And then we're going to add up the lengths of those line segments that we already know how to do, and that will approximate the length of the curve. Okay, so it's the same sort of technique we did with areas under curves. Right, chop up into smaller pieces, use something easier geometrically that we know how to do. Okay, so that's where we are. Now let me draw a little let me just pick a random line segment in the middle here. Right, so for example, like, you don't write this down, but this is like x naught, y naught, this is x1, y1, etc. This is xn, yn, right, it's f of x, it's f of xn, this is f of x naught, f of x1. But we're going to stick with x's and y's. So suppose somewhere in here I have two consecutive points, like these two right here. And let me draw that over here. So suppose we have a point here that's xi minus 1, yi minus 1. And then the next point over here is xi, yi. So these are two consecutive points here somewhere, like those two, or those two, or those two, or two here. Okay, so it's somewhere in the middle. Okay, so the curve is coming in here, and we're interested in the line segment joining. So I don't know, the curve is doing something, to do anything, as it goes to that point and that point. Okay, so let me make a right triangle out of that. And let's see, how do we find the length of the line segment? Well, we can just use Pythagorean theorem. Well, what's the length of the leg there? Right? Well, right, this has an x value of xi, and this has a value of xi minus 1. Right? So it's basically, the difference, it's the width of one of these intervals, right? For example, how far is it from here to here? It's x3 minus x2. Right? How far is it from horizontally from there to there? It's xn minus 1. So this distance is xi minus xi minus 1. Right? That x value minus that x value. And what about the y? I want that distance. Well, it's the same idea, right? Right? If I make a triangle here, what's that distance, the vertical distance? It's that y value minus that y value, right? So it's the higher, I'm going to put the higher y value. It's yi minus 1 minus y. Now you have to be careful here. Xi minus x minus x of I minus 1 is always going to be positive. Because xi is always bigger than the x before it, right? This x is bigger than the one before it, that x is bigger than the one before it. But this quantity could be negative, couldn't it? Right? It depends, right? If I take the y before, yeah, notice this y is bigger than this y, so that y minus that y is going to be a negative. Right? Whereas here, let me see, did I do that right? Y minus 1, the one before. No, that'll be positive, that'll be negative, yeah. So sometimes this quantity is going to be negative. But that's neither here nor there, because how would you find that? Well, use Pythagorean theorem. So whether that's positive or negative doesn't matter because we're going to square it. So that side squared plus that side squared is that side squared, right? If I just call that r, so what's r going to be? R is the square root of, do I want to be consistent here? Right, so the order that doesn't matter. So yi minus 1 squared plus xi minus xi minus 1. Right, as soon as I put the square on that, it doesn't matter which way I put it. Okay, so that's the length. All this work was to find the length of a line segment, right? I said we knew how to do it, and that's what we're doing. Just you can use Pythagorean theorem. Okay, so this represents the length of the ith segment here. Check that one say. Okay, so we're down to the bottom here. It says length of the ith segment is this. I've switched the order in the notes, but that's okay. Okay, so that's where we are. Now, just for ease of notation, we're going to call this delta xi, and this delta yi. So we've got delta yi squared plus delta xi squared. Okay, now that's just the length of one of the segments. So how do we estimate the total arc length? We just add up that one plus that one plus that one plus that one. And so we're down to where it says length of all segments. That's the sum I equals 1 to n of the square root of delta xi squared plus delta yi squared. Right? So that was just the length of one of them, and so we add them all up. Okay? So the length of all the line segments is this. Now that's an approximation of the arc length. Okay, so that's where we are now. Now we need to do some algebra here to actually get to where we want. All right, well, we do have a sum. Is this a Riemann sum is the question. Right? We want to get Riemann sum so we can do things with definite integrals. And I hope you realize the answer is no, for two reasons. Number one, there's no delta xi out here. Right? Remember, Riemann sum was f of well, it depends on what variable you want to use. You know, f of xi or f of ci delta xi. So we don't have a delta x out here, and this is not an f of ci. We don't have the original function here, right? If we call it f of x, we don't have f of ci, right? Or f of xi, whatever, however you want to do it. Okay, so let's do some algebra on this expression here. So we're going to continue here. Sum I equals 1 to n. Okay, square root of. So delta xi squared I'm going to leave alone. And I'm going to rewrite this as delta yi over delta xi whole thing squared times delta xi whole thing squared. Plus. Sorry. So I left that alone, left the plus alone. Now, do you agree that this whole thing here is the same as delta yi squared? Because this is delta yi squared. That's that. This is delta xi squared in the denominator times delta xi squared. They cancel. Okay? So they're certainly the same thing. So we made it more complicated, but we're doing it for a certain reason. Notice now I have a delta xi squared here and a delta xi squared here. So I can factor that out under the radical. So I still have my summation. So I have the square root of 1 plus delta yi over delta xi squared factor a delta xi squared out of both. So you factor it out of here, you're left with 1. You factor it out of here, you're left with the delta yi over delta xi quantity squared. That's a funny square root. All right, that's all I've done. Okay, and then lastly here, I'm just going to leave, now, so you have a square root of something times something, so you can break the square root. So we have the square root of that stays the same. But the square root of delta xi squared is just delta xi, because remember, delta xi is positive, right? That was that minus that, or that minus that, or that minus that. If you take the square root of something squared and the something is positive, you just get that right back. So the whole point of this was to start making this look like a Riemann sum. Remember, when I said, is this a Riemann sum, I said, no, there's no delta xi. Now we have one. That was the only reason for going through all that mess. Okay. Now, is this a Riemann sum? And the answer is still no, right? We have our delta xi, but this needs to be, you know, f of xi or f of ci in here somewhere, okay? Remember, the Riemann sum was the sum of f of xi delta xi, right? Or f of, you know, some c, f of ci, where c is some point, right? Some x value. And this doesn't look like that at all. But we're getting there. Okay, so I don't need this. So that's where we are. Okay, so now I'm on the top of the next page here. We made it through one page. Okay, so the length of the curve, now remember, this we're still adding up. That's still the length of the line segments. And so what would the length of the curve be? The length of the curve, which here they're calling little s, I have no idea why. Well, if we take the limit as the partition goes to 0, remember I didn't take an equal partition, so I can't just say n goes to infinity here. If you go back and look at, I think section 4.3, remember that's where we had to do this. If you don't take an equal partition, you have to do that. Remember what this means? The smallest interval has to go to, the length of the smallest interval has to go, of the largest interval has to go to 0. So when you start chopping this up into more and more pieces, you can't just chop here. See, if I keep chopping here, n is going to infinity, the number of intervals is going to infinity, but that's not going to give you the length of the curve, because this, you're chopping up and that's getting more and more approximate, but then you're not touching this at all, right? So this means keep chopping everywhere, that's all that means. So if I take the limit of that, that will be the arc length, right? Now, so we have a limit, but it's not of a Riemann sum, right? We're okay here, we got our delta xi, but we've got to get an f of xi and f of ci in there somewhere. Okay, so that's where we are, we're almost there. Okay, so, now, I say since the derivative exists for each x in one of the intervals, xi minus 1 xi, so just pick your favorite interval here. I say the derivative exists everywhere in between. In each interval, the derivative exists in between. Well, how do we know that? Well, remember, we assumed that f was continuously differentiable. So we're assuming f is differentiable, so the derivative exists everywhere. It says by the mean value theorem, there's a ci in the interval where f prime of ci is delta yi over delta xi, huh? Okay, let me just draw this curve again. All right, so we're in some interval, whatever. So I'm exaggerating here. This is one of the intervals here. So we have, xi and xi minus 1. So this is delta xi. So let me exaggerate this too. So the curve is doing something here. Okay? And then from here to the difference in the y's, that's delta yi. Now, think about what delta yi is divided by delta xi, right? Right, that's the slope. That's the slope of the line segment joining the endpoints, isn't it? Right? Change in y over change in x is the slope of the line connecting the endpoints. Remember, that's what the mean value theorem was all about. Right? If you have a a function continuous on a closed interval and differentiable on the open interval. Remember, we're assuming the function's differentiable everywhere. In fact, it's continuously differentiable. The derivative is continuous as well, right? So by the mean value theorem, there's a c in here somewhere, which we're calling c sub I, where the derivative is equal to the slope of the tangent line somewhere in the middle is equal to the slope of the line joining the endpoint. So this is the slope of the line segment joining the endpoints by the mean value theorem. There's a ci for which this is true. Right? So we're finally seeing where mean value theorem is coming into play. So notice what we can do here, right? For each delta yi over delta xi, so for each interval, we can replace this weird expression with f prime of ci. So instead of that, square root 1 plus, I can replace the delta y over xi with f prime of ci squared. Whew. So that's where we need mean value theorem. We got to get rid of this and get it as a function of something. Okay. Now look what we have. We have a Riemann sum. Right? We have our delta xi and we have a function where we're plugging in, a value in each interval. Now notice that's not f, it's f prime, but that's okay. Okay, lastly, so we're basically done here. There's one more thing to write. I'll just add it on here. Well, let's just cut to the chase. Okay. We have the limit of a Riemann sum. Again, there's a Riemann sum. I have my delta xi, and I have a function here where I'm plugging in a ci, right? A c1, a c2, a c3, a c4. And what is the limit of a Riemann sum? The limit of a Riemann sum is a definite integral. So this just turns into a definite integral. So we integrate from a to b, right? A to b. Remember, the delta xi becomes your dx, and then you're just left with this, the square root of 1 plus f prime of x. Remember that each of the ci turns into x squared. Okay, now I'm jumping the gun here a little bit. Now, how do I know this is? Remember, just because you have the limit of a Riemann sum, it's the definite integral. I mean, if the limit exists. Okay, now how do we know the limit exists? Well, remember we said f prime is continuous on the closed interval. That's where the continuously differentiable is coming into play. Right? So we know the derivative function is continuous. So f prime is continuous. Well, if you square a continuous function, you get a continuous function. If you add 1 to it, it's going to be a continuous function. And because it's 1 plus something squared, the radicand is never going to be negative. So the square root is not going to be a problem, right? If this had been 1 minus, we might have a problem because the radicand maybe could be negative, right? Right? If you take f prime and square it and add 1 to it, it's going to be a non-negative number. So, in fact, this can be at least 1, isn't it? So that's no problem. Right? So f prime is continuous, f prime squared is continuous, 1 plus f prime squared is continuous, and the square root of that will still be a continuous function. And we learned that a theorem in Calc 1 said if you have a continuous function, it's integrable. Okay? Remember, continuous function is not necessarily differentiable, but a continuous function is always integrable. So the point is, this is a continuous function. We know it's integrable, therefore the integral is going to exist. Okay, so that's where we need a mean value theorem. We just needed the function, the derivative existed to use that the mean value theorem to go from here to here. We needed the function, the f was continuously differentiable to go from here. Okay, so there's your formula for arc length. I know that was a lot of time and effort just to derive that formula, but there we go. Okay, so the arc length of a curve from x is a to x equals b is the square root of 1 plus its derivative squared, dx. Whew. Okay, let's do a couple of problems here. But I want you to see the theme. That's the theme we're going to be doing in this class a lot, is what we did in the first lecture, what we did here, deriving this formula. chopping things up into smaller pieces, doing something with the smaller pieces, adding them up again, taking the limit, and then passing to the integral, because the limit of a Riemann sum is a definite integral. Okay, we're going to do that over and over and over again. So I want you to realize, the general procedure. So number 10 says, find the arc length of the graph of the function y is 2x to the 3 halves plus 3 over the interval 0 to 9. Now they have a graph in the text of this. You don't need this. I mean, it's looking something like this. Okay, fine. You don't really need the picture. You get a different one. Okay. Okay, so to do this, what do we need? Well, we just use the formula, but what's important in the formula, we need the derivative, right? So y prime, the derivative of 2x to the 3 halves is, bring down the 3 halves, that's going to be 3x to the 1 half. Just 3x to the 1 half. Okay, so the arc length, I'm going to label little s. That's the integral from 0 to 9, right, it's 0 to 9, of the square root of 1 plus the derivative, 3x to the 1 half squared. Well, I'm just using the formula we just found out. Remember, it's not the original function squared, it's the derivative squared. Okay, so let's just keep going here. Well, 3x to the 1 half squared is just 9x, isn't it? Okay, so far so good. Okay, now how are we supposed to integrate this? Is this a straight integration problem? Remember, that's the first thing you ask yourself. And if it's not, what substitution would be reasonable? Well, the answer is yes. It is straight integration only because what would your substitution be? If I were going to work out a substitution, I would let u be 1 plus 9x, wouldn't you? Because then you'd have square root of u, which you can integrate. But if u is 1 plus 9x, notice that's a linear substitution. So it is a straight integration. We learned last time we don't have to work out the linear substitution problems. Okay. Again, if you want to think of this as the integral from 0 to 9 of 1 plus 9x to the 1 half. Okay. So if you let u be 1 plus 9x, you'd have u to the 1 half, which you know how to integrate. Okay. So I'm using our stuff with the linear substitution, right? So I'm asking this, think of this as the integral of u to the 1 half. What would that be, right? It's u to the 3 halves over 3 halves, isn't it? Add 1 to the exponent, divide by the new exponent, or 2/3 u to the 3 halves. Okay? So that's scratch work, which you don't need to put in your homework. Okay? So it's going to be 2/3 linear to the 3 halves, evaluated from 0 to 9. Okay. All right, the integral of x to the 1 half is x to the 3 halves over 3 halves. That's what I used here. So over 3 halves became 2/3. And now we just plug in our 9. That's 2/3, 82 to the 3 halves. Now be careful, just because you have a 0 doesn't mean you ignore it. You actually have to plug it in. Minus 2/3, 1 to the 3 halves is 1. Right? Even if 0 is an endpoint, plug it in and make sure you actually get something non-zero. Okay, and if you do that, oh, I made a mistake, didn't I? Did anybody catch it? It's almost correct. What did I forget to do? I did a linear substitution, but I forgot to adjust for the slope. You need a 1/9 out. Remember, it's 1 divided by the slope. There we go. Sorry. Completely forgot. I was so excited that this integration was kept complicated. I wanted to be careful, and then it didn't adjust for the slope. And this turns out it's approximately 54.929. Okay. And I gotta watch out for that adjusting for the slope. That's a common mistake, and I just made it. Okay, that one's not too bad. Okay. Okay, let's do another example. Number 17 says, find the arc length of the graph of the function y is 1/2 e to the x plus e to the minus x over the interval 0 to 2. And I put a note in the I added that in parentheses. This function is called the hyperbolic cosine of x. That's what the H stands for, is hyperbolic. This is the hyperbolic cosine. If you change the plus here to a negative sign, that's a hyperbolic sine, which is sin h of x. Now, when I was in school, my professor called this cosh x, and the other sinh x, and cosech x, and tanh x. I mean, that's what he called all of them. I asked a colleague here, I said, well, how do you say that? And she said, hyperbolic cosine of x. Oh, excuse me. So, I mean, I say cosh. Anyway, you don't have to know that. I just think that's something. There's a section in the book on the hyperbolic trig functions, I believe in chapter 5, so you might want to just look and see what those are all about. A lot of the identities that you have in trig, they don't all carry over, but there are a lot of similarities. Like, for example, sinh over cosh is tanh, for example. Okay, so that's just FYI. Okay, so they want us to find the arc length, so S, it's the integral from 0 to 2 of the square root of 1 plus. Now we need the derivative, which I haven't done yet. Let's do that, y prime. So it's 1/2. Well, the derivative of e to the x is e to the x. And the derivative of, you have to use chain rule here, the derivative of e to the stuff is e to the stuff times the derivative of the stuff, negative. So my original function here, y, was cosh x. This is sinh x. And if you take the derivative of this, you're going to get that. So that's one difference between hyperbolic trig functions and the regular trig functions, is the derivative of sine x is cosine x, the derivative of cosine x is negative sine x. The derivative of sinh is cosh, the derivative of cosh is sinh. You don't get the negative like you do in the trig function. Okay, so this is going to be 1/2 e to the x minus e to the minus x squared. Okay, now you need to be writing small because there's several steps here. So don't write large on this part. I didn't give you a lot of room. Wow, we got to simplify this mess. Okay, integral from 0 to 2, square root of 1 plus. Okay, well, we have to square this mess. Well, the half squared is a fourth. Okay, 1/4. And now we need to square this mess out. So we have to FOIL this e. Let me write it out here so you can see. So e to the x minus e to the minus x times itself. Right, that's what we're doing. We already did the half square. There's your fourth. And now we need to FOIL that mess out. Well, e to the x times e to the x is e to the 2x. And so notice we're going to have a negative. Now what's e to the x times e to the minus x, right? If you add the exponents, you get e to the 0, which is 1. So that's minus 1. And you do it here, you also get a minus 1. So that's minus 2. And the negative times the negative becomes positive. And then e to the minus x times e to the minus x, if you add the exponents, it's e to the minus 2x. Well, that's kind of strange. But that's what you get. Right? You do when you're foiling, and you do the outside and the inside terms, you wind up with a constant, which you normally don't get. Okay, let's clean this up a little. I'm probably I'm going to put extra steps you don't really need, but I'm trying to be careful here. Okay, we have a lot of constants floating around. I want to combine those together. But I have a fourth e to the 2x. And notice at the end here, I have 1/4 e to the minus 2x. And now what do we have in the middle for the constants? I have a fourth of negative 2. That's negative a half plus 1 is plus 1/2. Okay, let me do that again. So a fourth of that is that. A fourth of that is that. A fourth of negative 2 is negative a half plus the 1 is plus a half. Okay? Okay, we're getting there. And now I'm going to factor a fourth out of that whole thing under the radical still. So I'm factoring a fourth out of there, you get e to the 2x. Factor the fourth out of there, you get e to the minus 2x. And factor a fourth from the half, you get plus 2. Right? And you should always check your factoring by remultiplying. A fourth of e to the 2x, a fourth of 2 is a half, a fourth of that is that. Don't forget your 2 does. Okay? And notice I can break up my radical. I have a product here, a fourth times that mess. The square root of a fourth is a half. I can pull that out. Okay, now let's look at what we have left here. Look at this expression right here. E to the 2x plus 2 plus e to the minus 2x. Does that look familiar to you? It should, because it almost looks like this. And where did this come from? This thing came from the e to the x minus e to the minus x squared. And so it shouldn't surprise you that this has the same sort of form. Right? This came from something squared. That is almost this, so maybe that will come from the same sort of thing squared. And it does. Notice this is e to the x plus e to the minus x squared. Right? Because e to the x squared is e to the 2x, e to the minus x squared is e to the minus 2x. And when you do the foiling with the outside and the inside, you'll get e to the minus x times e to the x. That's 1, and then you do the outside and the inside, you get a 1 plus 1 is a 2. So that's the only reason. I know that's tricky, but only because you have to go from this step to this step. That it's not unreasonable when you get to here to realize that, oh, wait a minute, that can actually be factored. Okay, and so the good news here is, we're almost done. We have the square root of something squared. Now, in general, the square root of x squared in general is not x. Okay, if x is positive or 0, square root of x squared is 0. If x is negative, this is not true. Okay, the fact that you should just remember, the square root of x squared is the absolute value of x. Right, this is saying what's the positive square root of x squared. If x is negative, right, the square root of x squared, let me just show you. So suppose x is negative 3. If I do the square root of x squared, that's the square root of negative 3 squared, which is square root of 9. Now, the root's already in the problem. This says what's the positive square root. The positive square root of 9 is 3, which is not the same thing as x. The square root of x squared is not x if x is negative. So how do we fix that problem? Right? The square root of x squared is the absolute value of x. Right? And the absolute value of negative 3 is 3. So that's a fact you need to remember. The square root of x squared is absolute value of x. But if x is positive or 0, then the square root is just, you can drop the absolute value. And that's what's going on here. E to the x plus e to the anything is always positive. So this is a positive plus a positive, that's a positive. Okay? So the square root of that squared is going to be that. Okay? So the square root of something squared is the something as long as the something is positive or 0, which it is. Because e to the anything is positive. Now, if this had been a minus here, we'd have an issue, because e to the x minus e to the minus x may not be positive. Okay, now we can finally integrate. This was just all algebra. Right? I want you to realize there's no calculus here. We haven't done any calculus except for take the derivative. That's all we've done. Okay, so now we're ready to integrate. So the integral of e to the x is e to the x. And now what's the integral of e to the minus x? Well, it's a linear substitution, right? Let u be negative x, and so that's going to be the minus e to the minus x. Right, you have to do 1 over the slope. Evaluate it from 0 to 2. Okay, and so when we plug in 2, we get e squared minus e to the minus 2, minus 1/2 e to the 0 minus e to the 0. Okay, that's just going to be 0. So I don't need that. And so there you go. And that turned out to be about 3.627. Well, that one took a little bit of work, but it wasn't the calculus that was the problem. It was, doing all this algebra. But I want you to recognize, when we squared that, we got this expression, and something similar showed up here. That's the clue to just go backwards. Okay, that was the clue there. And again, going from here to here, right, I did the linear substitution. Right? The integral of e to the x is e to the x, so the integral of e to the linear is e to the linear, 1 over the slope. Okay? Okay, so the other idea in this section is on surface area. At the end of Calc 1, you did volumes, remember, with shells and discs. And so what was that? You took a curve and you rotated around an axis and you got a three-dimensional figure and you found the volume. It's the same idea. It's a surface of revolution. You're trying to find the surface area of the surface of revolution. So you do the same sort of thing. You rotate it around an axis or another line or something. You get a three-dimensional figure and you're trying to find the surface area. So what's the area of the outside? Okay, so I'm not going to derive the formula, but the definition says let y equals f of x have a continuous derivative, just like we had before for the arc length. The area S of the surface, now here it's capital S, it's given by 2 pi integral from a to b of the square root of 1 plus f prime of x, well, that's something that squared, r of x, square root of 1 plus f prime of x squared dx. Now I want you to notice that part right there is exactly the same as the arc length formula. That part's the same. The only extra term here, well, you have 2 pi, that's extra. And then you have this r of x up front. Now what does r of x stand for? It's the distance between the graph of f and the axis of revolution. Okay. And I say similar form exists if x is, this is if f of x, so y is in terms of x's. If you have a function x in terms of y's, you still have the distance from the curve to the axis you're rotating around, and this will just be the derivative with respect to y. Okay. Okay, so we're not going to derive the formula, but it'd be, I'm sure, the same sort of procedure we did before. So we're going to do 2 problems here. 4, he says, set up and evaluate the definite interval for the area of the surface generated by revolving the curve. Y is 2 root x on the interval 4, 9 about root x. Now, on the arc length problems, I didn't really need a picture to do those problems because nothing involved. You didn't really need the picture to use the formula. But because of the r of x here, I think I really need the picture here. But we know what root x looks like. It's just your half your sideways parabola, and multiplying by 2 is just a stretching factor. So as a rough sketch, it just looks like this. And we're going from 4 to 9. Okay. So imagine this piece here, we're going about the x-axis. So imagine this part rotating about the x-axis, and we're going to find the surface area of just that piece that rotates around. Okay? Okay, so what's the formula going to be? Well, it's 2 pi, integral from 4 to 9. Now, what's r of x here? Now, r is the distance from the curve to the axis you're rotating around. So what's that distance right there? So I always try to draw several to show it. Here it's not the same distance, right? So it's not a constant, it's not 6 or something like that. So right? Whenever you measure from the x-axis up, that's just the y value, isn't it? So it's just the y value, which is 2 root x. And then times the square root of 1 plus the derivative squared. Okay, so we just need the derivative. So y here is 2x to the 1 half. And I'm just rewriting that as x to the 1 half. And then y prime is, bring down the half, it's x to the minus 1 half, isn't it? Okay. Okay, so the setup here is not that hard. But again, I drew the picture to help me see what r of x was. Right? R here is the distance from the curve to the axis you're rotating around. So that's just the y value, which is 2 root x. Okay, let's do some simplifying things before we integrate. I can pull the 2 out front and make that a 4 pi, no problem. Now square root of x times the square root of 1 plus, now x to the minus 1, I have squared base to a power to a power, you multiply the powers, I get x to the minus 1. Okay. Do you have an idea of what to do now? Substitution? And that x to the minus 1 is a pain, is it not? I think I know what I would do. I have a root and a root. Let's just multiply the roots together. Square root of a times square root of b is square root of ab. So you just multiply x times 1 is x, and x times 1 over x is 1. Right? So I just combine the roots. So if you let u be 1 plus x minus 1, you're not going to get it to match the way you want. I mean, I say, maybe it'll work out, but I think this is much easier to do what I just did. Okay. Now it's just a matter of doing the work here. Okay. How are we supposed to integrate that? Square root of x plus 1. Well, again, if you let u be x plus 1, you'll square root of u, which we know we can integrate, but x plus 1 is a linear substitution. Okay? This is why I taught the linear substitution in the review, because it shows up all the time. Okay? So again, think of this as x to the 1 half. Right? What would the integral of x to the 1 half be? Be x to the 3 halves over 3 halves, or 2/3 linear to the 3 halves. And then I'm not going to forget to adjust for the slope this time, but the slope is 1, and so 1 over 1 is 1. You don't really have to adjust. And then evaluate it. Right? So again, what I was saying here is basically, what's the integral of x to the 1 half? Right? It's x to the 3 halves over 3 halves, which is 2/3 x to the 3 halves. So 2/3, so the integral of x to the 1 half is this, so the integral of linear to the 1 half is this, right? You put the linear expression in for x. And again, adjusting for the slope is 1 over 1, so you don't have to do that. And now it's just a matter of plugging in. So I get 8 pi over 3 times, if I plug in the 9, I get 10 to the 3 halves. Minus 8 pi over 3, plug in 4, I get 5 to the 3 halves. It's about 171.25 square units. Okay. Okay, so that was that one. One more. But see, the setup's not hard. I want you to realize where all the work is. All the work here is in the integration. So you have to practice your integration. You'll be practicing your integration from Calc 1 as you work through problems. Okay, number 46 says, set up and evaluate the definite integral for the area of the surface generated by revolving the curve. Y is 9 minus x squared on the interval 0 to 3 about the y-axis. Okay, well, let's get, again, to find that r of x, I think I'm going to need a picture. But I know what the graph of this looks like, right? Well, just do your transformations. You know what y equals x squared looks like, your basic parabola. minus x squared is the reflection of that over the x-axis, plus 9 says move that up 9. So you don't really have to, again, a rough sketch is fine. So I said my y equals x squared, y equals minus x squared, y equals minus x squared plus 9. Okay. And notice where the x-intercept is, right? When x is 3, you get y is 0. So this is that 3 right here. So we're going from here. So it's this piece right here, and we're revolving about the y-axis. So we're going this way. So basically you get this little bowl. And you rotate that around with this bowl. So we want the surface area of the bowl. Okay? Okay, so the surface area, don't forget 2 pi, and that goes from 0 to 3. Now what's r of x? R is the distance from the curve to the axis you're rotating about. So now we want this distance. Now how far is it from the y-axis over to a point? That's just an x value. That's just x. So the r of x here is just x. And then we have the square root of 1 plus the derivative squared. Now what's the derivative? Y is now minus x squared, so y prime is minus 2x. Okay, so if we do some simplifying here, 2 pi, and we'll go from 0 to 3 of x times the square root of 1 plus 4x squared. Okay, so that's where we are. So the setup isn't that hard. So how do we integrate this? Okay, you can't just put that in like we've done the last one because there's no radical here. It's not a root times a root. But this is just a substitution problem, right? Let you be the radicand, right? We have a square, so when you take the derivative, and it doesn't quadratic, when you take the derivative, you're going to get a linear. Okay? But notice this is not a linear substitution, so I'm just going to work that out. So let u be 1 plus 4x squared. So du is 8x dx. Now, I don't have an 8x. Again, I like to make this match what I have in the problem. I just have an x. So I'm going to multiply both sides by 1. I'm just going to continue up here. Okay, so I have my 2 pi. Okay, I always substitute for this first. So instead of x dx, I get an 8th du, so there's my 1/8. And I go du. So all I've done is I've only taken care of the x dx. And now what am I left with here? That's square root of u, or u to the 1/2. Which is something I can integrate. And notice I don't mess with the endpoints till the end, because if I do the substitution and this turns out to be something I can't integrate, I've done a bad substitution. I have to try something else. So I always do change the endpoints last, because there's no point changing endpoints first and then you realize you made a mistake with the substitution. So I'm going to change my endpoints now. So when x is 0, what's u? Well, when x is 0, u is 1. And when x is 3, that's 37. U is 37. Again, once you change the endpoints in a substitution problem, you don't have to go back to x's now. Okay? So when x is 0, u is 1. When x is 3, that's 9 times 4 is 36 plus 1 is 37. Okay, now it's an easy substitution problem, easy problem. 2 pi, that's pi over 4. And the integral of u to the 1/2, God, how many times are we going to do that? That's u to the 3 halves over 3 halves, which is times 2/3. We're going from 1 to 37. So this is just pi over 6. That's 37 to the 3 halves minus 1 to the 3 halves, which is 1. And if you want an approximation, that's about 117.31. Okay, so that's section 7.4.